Yeah, and thank you so much for the invitation. I can't see many of you, so I will just pretend that there is I think I see only the last speaker. But that's absolutely fine. I wasn't able to come to Chaos for this workshop. It's quite a shame. And I'm currently sharing my office with about 150 exams. Oh, I can see you, Eric. I currently share my office with about 150 exams that I have to mark. But I'm still very happy, of course, to give a talk, and maybe I can. Oh, hi, Raoul. And maybe I can manage to come to next year's edition. I also know that I'm the last one before the fish restaurant, and I really like the fish restaurant. So I will try to not overrun too much with my talk. I want to tell you about something about losing momentum in continuous time stochastic optimization. And this is, of course, like supposed to be a sort of funny title, because obviously I don't want anyone to lose momentum in continuous time stochastic optimization, because it's a topic I'm very excited about. But within an algorithm, it can sometimes make sense. And I want to tell you more about that in the next 45 minutes or so. First of all, this is joint work with my friends here. So that would be Keshin Jin from Princeton, Shengo Liu from Delft, and Alessandro Scagliotti from TU Munich. And I will tell you mainly things about this paper, this preprint up here, with these three people and myself that have having authored it, and like a bit of background from this old paper down here. That I've presented at a Chaos online seminar, I think like 2 years ago or so, maybe. So I will try to keep that brief, but obviously not everyone here has seen their talk, so I will give you enough background from there to understand the paper up here without any problem. There are other works that sort of follow similar lines that I've cited down there. I will also later send you the slides, and kind of most of these references are clickable. So we will find all of them online. Exactly. So here's a bit of an outline. I want to start talking to you about optimization and data science, so to highlight the challenges of this methodology, and show you why what we will be doing then is of importance. Then to introduce this methodology and to give you more background in this area of research, I will be talking a bit about classical mechanics and continuous optimization. My knowledge of classical mechanics is very, very small, so I'll try to keep that brief, but it's a nice motivation for how these algorithms work, so I still want to tell you things about this. Then the main part would be the stochastic gradient momentum process. That is a stochastic process that represents stochastic dynamics that use momentum in optimization, and that we will analyze, or that we've analyzed in this paper that we'll talk about. And then tell you a bit about implementation and like one very small numerical experiment where we train some neural network, and some conclusions at the end. Now I know that this is a lot, so I actually put the take-home messages on this slide as well. So just so you know what you should be looking out for. So after this first section, you should have learned that that big data and non-convexity make optimization data science very difficult. In the second section, you should have learned that optimization methods can sometimes be studied through, say, more or less classical mechanics. Then this stochastic momentum process, I call it SGMP, is a good tool to explain momentum-based stochastic optimization. It approximates gradient flows, underdamped gradient flows, and the stochastic gradient process that I will tell you about. If we lose momentum, and that's kind of the title of the talk, and I will introduce this in just a few moments. We can actually find a minimiser in a strongly convex optimization problem. Which is a bit hypocritical when talking about non-convexity here, but I hope I can still motivate this. And then if prescribed properly, we can actually use this method for deep learning and for convex optimization. I don't actually show you experiments about convex optimization, so you have to believe me in that regard, but I show you some nice deep learning example. Okay, but let's get to the talk. Optimization in data science. So what I would like you to think of throughout this talk is that we want to minimize the function of this form. So a function I call it phi bar, and phi bar is given as a sample mean of several phi I. Okay, and we always minimize on R to the n. I believe you can probably also generalize these things to maybe several Hilbert spaces or so, but we haven't done this. But I think most of the results are probably more generally true. And we assume that these phi i's are sufficiently smooth. Yeah, so at least say like once continuously differentiable is what we certainly need. But if you do like L1 minimization or so and you're not quite there, then this may sometimes be fine as well. And of course, what you should think of is phi bar some kind of potential, say in statistics would say negative log likelihoods, and machine learning would say it's a loss function, given with respect to a large data set. Yeah, so you could say, okay, we have a data set that has like n many entries. Okay, and we need to minimize our negative log likelihood with respect to these like n different entries, and n entries would be n independent samples, for instance. Then we get this long sum, and every single one of them represents like a single data set. Okay, in imaging like a single pixel, for instance, and the whole sum then represents the whole image. Okay, but this is like a very basic structure. If you have an optimization problem that has a large sum here and that has nothing to do with data, yeah, that's also absolutely fine. But I just like to think about this data setting. Let me give you some examples. So, for instance, in image reconstruction, you could think of this particular problem. So, what happened here? I believe NASA sent up the Hubble telescope into space, and they've noticed when they looked at early images that it's very blurry, because there was a problem with one of the mirrors. And then, yeah, I mean, once up in space, it's not so easy to fix it. Okay, so you could be wondering, okay, how can I turn this blurry image into a sharp image? So what they did here is they actually fixed the flaw in the mirror by, I think, essentially putting glasses, like literally some like lens outside on a telescope to fix it. But of course, you could also try to see this as an inverse problem and then try to actually reconstruct this. In that case, the minimization problem would look a bit like this. Yeah, so here we would sum over pixels. We have some say like convolution operator here, just some matrix that represents the blurring. Yeah, so yi is a single pixel that we observe, and theta is the whole image that we would like to get. Okay, and then this say it's Gaussian blur, so this is like super ill-post, which means that we need some regularization, which we could just call like reg here and assume it's smooth. Otherwise, it doesn't satisfy our assumptions. But that would be a very basic problem that you could think of in this setting. A different problem would be supervised learning. So here the very basic setting is we have some random variables x and y that have a joint distribution, and we would like to be able to predict y given x. Okay, I'll give you an example in just a moment, but that's just a general prediction problem given pairs of random variables. And how we do this in machine learning usually is we say we find a parametric model. Okay, so we say we have some parameterized function f hat, and we have a lot of sample data. Okay, so we have some samples of these xy random variables, and we would now like to find f hat by finding the theta, or by minimizing this target function over theta, such that f hat represents this prediction as well as possible for these observed data pairs. Okay, and and here I have an L2 distance, but this could also be something more general. So for instance, in this case, the L2 distance wouldn't make much sense. Yeah, where we say, okay, we have pairs of images and labels. Okay, so this image shows a cat, that image shows a frog, that image shows an airplane, or it's at least supposed to. And we would now like to find a function that takes one of these images and returns the label. Yeah, okay, in that case, obviously, we can't really compute sensible L2 distance of a label. So you probably want to use cross entropy or something like this. That makes more sense for classification problem. But if you want to think of linear regression, Yeah, that would also be an example for this, where f is just a line, or polynomial regression, where f is a polynomial with parameters theta. That's fine as well. But obviously, this gets more interesting from the optimization perspective if this is something as complicated as such data set. If we have such a data set, usual model would be a deep neural network. Okay, that looks somehow like this. Yeah, so we say, okay, the output is our f big K. We get f big K recursively through this process. Okay, so we have to our fk minus 1, we apply a matrix and we add a bias vector. So this is completely linear. And then we plug this into something nonlinear, like a so-called activation function, which, yeah, like very often is something very simple. Yeah, like essentially like a smooth, like a thresholding, something like this. But also there's a huge choice. And then we try to estimate. We do this a couple of times. Yeah, that's why it's called deep neural network, because we have multiple layers. And in that case, our parameter theta would be a set of all of these so-called weight matrices and bias vectors. Okay, and then we would try to find them via such a minimization problem. Okay, but this is also just it's just one example. Yeah, many other problems are possible. Okay, so how do we minimize phi bar? Okay, and phi bar, as I said before, is given as this mean of these phi i's. First idea could be gradient descent. Okay, so we assume that phi bar, or actually phi i's, are continuously differentiable. So what we should be able to do is from our current position, theta k minus 1, we just do a step in negative gradient direction, yeah, with a certain step size eta k, and then this goes back to Cauchy. And basic theory tells us that if phi bar is convex, and if there is a minimiser, or maybe it's like strictly convex or strongly convex, but convex and minimiser is actually sufficient, and the step size is sufficiently small. Yeah, so that depends on the Lipschitz constant of this thing usually. Then we will converge. Okay, now that's great, and so we could just end the talk now, but okay, what could possibly go wrong? The first problem could be that n could be very large. Okay, and in these examples that I just told you about, like when you think of an image classification problem like the Cypher-10 problem, you would assume that n is like 10,000 or 50,000 or like 100,000. That would be quite normal. And then, of course, if we need to compute the gradient of the sum of many things, then what we get is a sum of many gradients, meaning we did many gradient evaluations. Okay, and that's very expensive. The other problem could be that phi bar could be non-convex. Okay, so here we have theory for the convex case. We don't really have theory for the non-convex case. Unfortunately, especially in deep learning, so this problem with these weight matrices and bias vectors, the problem will always be non-convex, or almost always be non-convex. These imaging problems, I mean, the one I showed you is certainly convex, but there are also imaging problems that are non-convex as well. Yeah, usually they're convex, though. Most of them are convex, but there are many that are non-convex. Many non-convex examples as well. But I think deep learning is the usual example for non-convex problem in this regard. Okay, so what can we do if n is large? So the basic idea would be stochastic gradient descent. And this is going back to Robbins and Monroe. Here the idea is we still go into negative gradient direction, but rather than taking the gradient of phi bar, we now just take the gradient of a single data set, or maybe like a sum of a few data sets. That's fine. I never really discuss it, but that's sort of in here as well. And I always call it subsampling because it is kind of taking a data subset, even if there's no underlying data set, we just have a large sum. I would say call it subsampling to make it easy. And so what we do is in every step, we pick one of the indices uniformly at random, and then we just walk in that direction of that index. Now this eta k is not called learning rate or step size. And it's not sufficient to have it sufficiently small, because I mean, the problem is when it's just like small, you will always have like a bit of movement still, because there's still a bit of randomness. What you actually need to do is you let it go to 0 over time. Yeah, so you need to get the variance down as this thing converges. And we now need them to be strongly convex. Okay, so we need even more regularity than before, where convexity and existence of a minimiser was sufficient. Okay, but let's say I mean, data sets essentially fine. So n could be large. That might still be okay. What if phi bar is non-convex though? So the obvious problem is, if phi bar is non-convex and we use gradient descent, is that what gradient descent finds is a point where the gradient of the potential is 0, and then it stops because it doesn't move anymore. And of course, this could be a saddle point or local extrema rather than a global minimiser, like in a convex function. Stochastic gradient descent does not necessarily get stuck because there, I mean, we always have this bit of randomness. Okay, so even if we hit a point where the gradient is 0, there's still a chance to get out of there. Okay, I mean, unless, of course, all of these terms in the sum of gradient 0, that would be a problem. But that's, say, it's not very likely to happen. Especially if you have noisy data, it's probably impossible to happen. But it's still not great in non-convex settings, yeah. So it's still rather slow at getting out of minimizers if it even gets out. Maybe one example here. So this kind of is a bit of a cooked-like example, but it's nice because we have one global minimizer here, and we have one saddle point here around 0. It has this non-smooth point here, so it doesn't really satisfy our theory, but it's good to play around with. So we're still using it here. So what happens if we use gradient descent for this problem is quite obvious. Okay, we start at -1, and so we start up here, and then we slowly go down, but then once we're at 0, we are just stuck. Okay, so we can't move out of 0. If we have an absurdly large step size, then okay, we could jump out of 0, but then I mean, we wouldn't ever find 0.5 either, because the step size is too large. Then I used stochastic gradient descent, and what I saw was actually quite exciting, because here when we start with the same point and we let the step size reduce as 1 over k, which would satisfy the theory. Then what happens here is we actually go to 0, and then we're stuck for a moment, but then we actually jump over the point, just because we got the right subsample probably, and we jump over it, and then we converge to 0.5 where the minimizer is. Okay, but it's a random algorithm, so I did it again, and it worked again. Did it once more, and it didn't work. Okay, so this time I just got stuck in 0. So I tried again, it worked. I tried again, it didn't work. Okay, so it is sometimes possible, but it's not very convincing as an algorithm for this sort of problem. So the question is what else we can do, and to sort of elaborate on that, I want to talk a bit about mechanics. Yeah. So first of all, how do we get from algorithms to mechanics? And the first idea is that we sometimes, okay, I mean, we see the algorithm sort of as something that actually generates a sequence, of some like these like psi k here. Psi didn't appear before, so I use it now as a letter. And it's sometimes possible to actually represent these like discrete time sequences by continuous in time processes. Yeah, so maybe like replace a discrete time sequence by, say, like an ODE, like here. And there's several reasons for why we would be doing this. Yeah, so like one thing could be that, okay, we are trying to get a general idea on how this algorithm works. And their discrete in time processes have like very particular behavior, for instance, like for large step sizes. Okay, so it could be that we first need to spend a long time understanding the stiffness of a problem, or understanding the step size behavior of a problem, before we really see what is going on. And then, okay, whilst application step sizes are very important, to get a general idea of a convergence behavior, it's really not so important. Yeah, the other thing is that in discrete settings, there are sometimes things that are harder, or there are things that are hard to see in discrete settings, or that are only visible when you're in the continuous setting. So I mentioned this deconvolution problem before. Yeah, we tried to deblur an image, and we noticed, okay, such a blurring matrix has an awful condition number. Okay, what we say, okay, maybe we can fix this with a preconditioning. Yeah, I mean, if we look at the operator that corresponds to the matrix, so we map this from a discrete space to a function space, or from a finite dimensional space to function space, then we actually see that the convolution operator has like exponentially decreasing eigenvalues. And then we see, okay, there's not actually much we can do. This is just a terrible operator, and there's nothing. But you wouldn't see this with the matrix. Yeah, you can only see this with the operator. But there's not much you can do in terms of preconditioning or anything. But you need regularization. What I like particularly is that we can suddenly understand algorithms a bit like we understand physical models. Okay, so we can say, okay, this algorithm behaves like that. Can we maybe find a physical behavior that we would find more favorable for this algorithm? Yeah, whilst the current physical behavior is one that we don't see. And there's many examples where ideas like these have been used. I mean, especially PDEs have been used in image reconstruction and data science, but obviously everything is discrete, but the PDEs are easier to analyze. Yeah, continuous time analysis in MCMC, continuous limit of graphs, where you say, okay, obviously your data is on a graph, but then maybe you can see your data as a continuum, yeah, as a weird manifold. Yeah, data assimilation. I mean, in the end, in data assimilation, you will always be in discrete time because your data comes at discrete points. Yeah, but maybe you get sufficient amount of data that would be okay to see as a continuous data stream. And then other optimization methods, or called optimization methods now, I mean, it's actually methods for inversion that have also been much, yeah, where the continuous time setting has been a very interesting object to actually analyze. Okay, so now what I would like to do for the next few minutes or so is I take these algorithms we just learned about and turn them into continuous time. And the first one is gradient descent, where if we look very closely at it, we actually see that this is a bit like an Euler discretization. Okay, so eta k is a step size, and we just do sort of do like one Euler step, one forward Euler step, and then we get we let eta k go to 0, so go to 0, and then we get our usual ODE, which is a gradient flow. Okay, and then obviously analyzing the gradient flow might be easier than analyzing the ODE, and we can get some information about our optimization method from the ODE. Like purely physically, this gradient flow now says, or this would tell us that that gradient descent essentially models the position of a massless particle, yeah, like a photon, I think is a massless particle. And the velocity of the particle is given by the negative gradient of the potential at the point where we are in space at that time. Okay. For stochastic gradient descent is a bit more difficult because there's at least two ways that I know of to do this. So first of all, if we take SGD and we let eta k go to 0, like we did before, and we rescale our system in the correct way, what we get is a diffusion process. Okay, so we still have sort of this first part looks a bit like our gradient flow. It looks exactly like our gradient flow. But then what we get is a noise part that contains multiplicative noise here. So these like sigma matrices are essentially cross products of these of the phi i's. So it's a bit like a variance actually, which makes sense. And that's a limiting equation for our SGD. Now, if we just let eta go to 0, we don't rescale because you see that eta still appears here. If we let just eta go to 0, we actually also converge to the gradient flow, but then there's no randomness in it, and maybe that's not a good model in continuous time to analyze this. What this means physically is that we still have a massless particle in an environment with many other particles, and we say, okay, the particles have a certain drift, yeah, so they drift essentially like the gradient flow before. But now we say that we have other particles and there are interactions with these other particles that we don't want to model one by one. So we just model them with this white noise term here. Okay, so this is like the predominant model, and okay, I'm mentioning like, I don't know, it's like 10 papers or so here. But there's probably like 100 papers or so out on SG analysis using this particular model. Now in this paper I mentioned earlier, I proposed a different approach that will just explain very briefly because it's kind of important for the next step. And because so when I look at this particular model, what I see is kind of two things that I see as a small issue. Yeah. So the first thing is we let eta go to 0. That sort of means we assume that we subsample at an infinitesimal rate. And you can say, okay, that is okay, it's just a model. Yeah, you will never be able to do that. But actually in SGD, we kind of try to exactly not do that. Yeah, but we try to have big steps, and actually many people actually leave eta constant even until the end of the algorithm, because I mean, like, okay, in the example I showed, we let eta go to 0 as you have to do for the theory. But actually, if you look at machine learning practice, it's very typical to just leave eta constant, and you still have these oscillations until the end. So you never get into the setting of like infinitesimal noise, which, to be fair, if this is positive, this is non-zero, then you also have noise, but the noise is very different from the noise that you would usually expect. The other problem is if you look at this SDE, then here we still have the gradient of phi bar. Okay, and I mean, okay, there are probably efficient ways to still discretize this, but I would actually like to see an SDE that does not depend on dynamic system, does not depend on phi bar at any point, because SGE doesn't either. Okay. So in this stochastic gradient process, what we essentially do is we have an ODE with the right-hand side that changes over time. Okay, so we say this is our stochastic gradient process that is theta dot is given by minus gradient of phi I of t, theta of t. Now I of t is a continuous Markov process. So there's a process that stays somewhere for a certain waiting time. The waiting time is random and jumps to another state after the waiting time is over. Okay, and here what we will do, okay, I will tell you more about this process in just a moment. But this process essentially decides which data set is picked at what point in time. Okay, so here in the beginning we say, okay, we take data set number n. We start with data set number big N. And down here, we then follow the ODE or the gradient flow that corresponds to this particular data set or subdata set. Okay, then we jump here, say to data set number 5. Then we follow the ODE that corresponds to data set number 5. Okay, so we get a kink here because we very abruptly change direction, obviously. Then we jump again to say data set n-1, which now again lets us abruptly change direction to go down, and so on. Now, from a physical perspective, this could now be a massless particle that sort of moves around in a randomly changing landscape, which is a bit strange. Maybe landscapes don't change randomly that much. But there is a better biological interpretation for this that I will not explain now, but it has to do with clonal populations that grow in randomly changing environments. Yeah, so this happens quite a bit in practice. In physics, maybe not so much, but I don't know. Okay, so this process, of course, what is wrong about this process? So the first thing that's wrong about this process, of course, is that that in normal SGD, these waiting times between jumps are always deterministic, and they're random here. What could be wrong is we haven't really discussed how we choose these wait time distributions, and there's sort of two different settings that I usually consider. One is with a constant learning rate. Yeah, so there's a mix-up. This should be a J probably. one is the constant rate where we say, okay, our process I from before is given just by a homogeneous continuous Markov process that we rescale it, that we potentially rescale in time, but in a homogeneous way. Okay, so you should think of this I in this case a bit like a Poisson process, just that we don't go up after every jump time, but we go to any other state at every jump time. And then what we can show under convexity assumptions is that we actually converge to a stationary distribution. Yeah, so theta converges to a stationary distribution. And we can also show that that theta converges weakly to the original gradient flow, yeah, as the step size goes down. So we can actually approximate this gradient flow as well. But this is the constant learning rate case. Okay, I call it constant learning rate because the distribution of this Markov process doesn't change over time. Okay, so at every point in time, we just draw an exponential random variable that decides when we jump next. Okay, so that's the only that is. I mean, still the jump times they may like change, but the distribution is the same. Yeah, so that's what's homogeneous about this. But now, in order to converge to a point, we actually need to decrease the learning rate. And we do this here in the following way. So first we say, okay, that J is still our continuous Markov process homogeneous, yeah, with jump rate 1. But what we do now is we rescale it in a nonlinear way. Okay, so here was just linear, so this is still a homogeneous process. But here we rescale it now in a nonlinear way, and it is a way that gives us shorter waiting times, or that sort of gives us shorter mean waiting times, I should say, as t goes to infinity. Okay, so here, I mean, this looks very much homogeneous, but in this case down here, these waiting times should get smaller and smaller and smaller and smaller as you go on through the process. And indeed, we can show under convexity assumptions that we converge now to the minimiser of phi bar. And so we actually match the theory for S3D in this case. Okay. But this is not supposed to help us when phi bar is non-convex. And the idea for the rest of the talk will now be is that we should give the particle that appeared in all of these processes, we should give it some mass. Because if the particle has mass, then it doesn't matter that like we hit a local minimiser somewhere, or we hit a settle point, or maybe local maximum somewhere, because we should just have enough energy or enough momentum to just like jump out of this minimiser. That's what we look at now. So the gradient has mass. We get an ODE of this form, and this is now just a deterministic setting. Okay, we have our position, we call now x. The position has a certain velocity. Okay, that's what this first equation says here. And the velocity times mass, okay, so m is the mass of the particle, is given as minus the gradient of phi bar at the position, minus alpha times v of t, so minus alpha times the velocity of the particle. And this alpha, we call it friction. It represents the friction. I will tell you more about the friction in just a moment. But this is now the ODE we will look at in the following. And this idea is really, really old. Okay, so that is works by Polyak and Nesterov. Yeah, so I think this might be the heavy ball methods. I'm not an expert in these, so please don't quiz me about them. But this has been around for a very long time, this idea, especially in convex optimization. So what is interesting with this, call it underdamped gradient flow, I'm not sure whether this is the right word for it, but what is interesting is that if we let m be 0, so let the mass be 0, we actually get our momentum case back. Okay, so you can just plug in 0 here, and then you see that, okay, now this should be equal to that. Yeah, and then that is just, okay, some prefactor times this. Okay, so you can just move this over here, and okay, you need to care about the alpha somehow, but you're essentially back in the non-momentum case. If we set alpha to 0, then we should actually conserve energy in the system, which is not great optimization. I will show you why in just a moment, because we now go back to our example from before. Okay, so it's still the same function. What I did just here is I started at -1 again, and yeah, it shows some parameters. So we start without velocity. We just start up here, so we just have potential energy to sort of fall down here. Mass is equal to 1, and friction is equal to 2. What we see now is we're still stuck in a settle point here. Okay, so this didn't really help. If we now reduce the friction though, then we suddenly, okay, we do slow down quite a lot when we get into the settle point. Okay, you see the velocity is actually getting slow, but then we just have enough momentum to just like fall over it and actually then get stuck in the actual minimiser. Okay, so that's like the optimal case. Yeah, so there's nothing to complain about. If the friction is like a bit smaller, then okay, this is now almost like we don't even notice settle point now. I mean, there's like a very, very small kink maybe, but maybe I'm just exaggerating this now. And then what we see here, okay, then we fall into the global minimiser, and then we oscillate a bit. Yeah, because we still have some energy, some momentum, so we need to sort of oscillate a bit here until we finally converge. Okay, but that still works really well. If we make the friction even smaller, what we see is, okay, we just overshoot the settle point. We don't notice it at all, but then we go back up, and then we go back down, and then we go just about back up, but not quite back up, and then we're just stuck in the global minimiser. But we see here already the friction is now rather small. Yeah, so therefore we have time until we actually reach our minimiser. Okay, because obviously we hit the global minimiser many times, but we never stop because we have too much. We have too much energy. And then okay, if we set alpha equal to 0, and that's what I said, it's not great optimization. We don't lose any energy. Yeah, so we will just always oscillate back and forth, yeah, we'll never converge. Okay, so I mean, okay, we could just say, okay, we're tracking the trajectory, and we then plug them back into phi bar and take the value that is smallest. Okay, could do these like tricks, but kind of in 1D everything's easy, but then in multiple dimensions, that's probably not possible. Okay. Now, okay, of course, the £5 million question is, what if phi bar is non-convex and n is large? And that's a question that has been around for quite a long time. And I believe at least Adam might be argued that some of you have heard of before. It's incredibly popular. But of course, you can now say we combine these two ideas. Yeah, so we do subsampling and we use momentum. Okay, so we kind of stick the subsampling idea in the new ODE and then use that new ODE. Unfortunately, this combination of subsampling and momentum seems to be difficult because they, to some extent, they both sort of accelerate and prevent convergence in a certain sense. Yeah, so they accelerate convergence because of their sort of kind of very. I mean, we get very closely to the areas like sort of close to the minimiser. Okay, so getting into the sort of periphery of the minimiser quickly is possible with both these methods. But then once we're in this like small area around the minimiser, we're actually rather slow. Yeah, because when we subsample, then we always have a bit of variance left. So we have randomness left, which doesn't really help at all in this particular setting. Okay, so what I've seen people do actually is using Adam for a few thousand steps to get close to minimiser, and then use Newton's method, for instance. Yeah, so because this is a big problem that you close to the minimiser, you don't really converge quickly. With momentum, the problem is, I mean, you already have this energy, you have this momentum left, and you sort of need to get rid of it before you can converge. Okay, so you will always like oscillate a bit until you finally stop. So we have these like two processes that sort of help us converge and also prevent us from converging. And we kind of need to see how we can balance them out to some extent. The other thing that is difficult is once we have discretized the momentum equation. yeah, then okay, these seem to, okay, first of all, discretizing these equations is not so easy. Yeah, you cannot really use Forward Euler. We'll talk about this later. But then like long-term behavior and things seems to be particularly difficult to analyze. But we'll see that in a moment as well. And that is for the next like 15 minutes of the talk or so. We'll talk a bit about the combination of these two. And now that you've seen all of this background, okay, it's like very long backgrounds, was a very long background section, but this will be very easy to understand now, I think. Because of course the idea is to now just say, okay, we take this momentum ODE and we plug in our subsampling algorithm. Okay, and one addition to before is we now allow the mass to depend on time, which that doesn't really make much sense. Yeah, so the mass of object usually doesn't change over time, but it's something that we hear. Okay, I mean, you can think of it. Okay, you can think of a pendulum that's could be like a sandbag, and it's like some sand is getting lost over time. You could think of something like this. And of course, the title of the talk is losing momentum. Yeah, and that's the whole idea. Because not only do we allow different index processes now, yeah, so again, the one that is constant or that is homogeneous, presenting constant learning rate and a decreasing learning rate, we also allow a constant mass, yeah, where does not depend on t, or a decreasing mass, yeah, where the mass goes to 0 as t goes to infinity, which would be the losing momentum setting. Now there's two types of results we want to show. So the first one is we want to show that our stochastic gradient momentum process, that's the thing that we just defined, that it is close to the underdamped gradient flow if we sort of lose stochasticity. Yeah, so if we make the subsampling go faster, that is, it's close to the stochastic gradient process if we lose mass. Like before, where we said, okay, we go from underdamped gradient flow to gradient flow by letting the mass go to 0. And then we go to the gradient flow if we lose both stochasticity, like the randomness, and the mass at the same time. Why is it helpful? All of these three processes seem to be much easier to analyze than a stochastic gradient momentum process. So at least if we know kind of how we behave at these limiting behaviors, we may be able to understand better what happens to this process. The other thing we want to know is what is the long-term behavior of our process? Because I mean, we're still talking about optimization methods, so we want to know is do we converge to a minimiser as t goes to infinity? And we'll show a setting where we indeed converge to a minimiser as t goes to infinity. That's now I always say at this point is where the hypothesis begins. Because we assume some smoothness for the phi i's, that's fine, but we also assume strong convexity for them, at least when we say long-time behavior. For the approximation, we don't need this at all, I think, but with a long-time behavior, then we need to assume that we are strongly convex, which of course kind of sort of defies the original idea. But then, as I said, these processes are kind of complicated in non-convex situations. Okay, let's talk quickly about the approximation. So we're in a setting where we have a constant learning rate. Okay, so the process I is homogeneous in time, and we assume that phi I satisfies the smoothness assumption. And what we can then show is essentially what this figure says, namely, if you have a positive mass and a positive learning rate, then we are in a stochastic momentum process. If we let the mass go to 0, we converge to the stochastic gradient process in the supremum sense. If we let the stochasticity go to 0, yeah, stochasticity go to 0, meaning we subsample extremely often. Yeah, so this process jumps really, really quickly. We go back to the underdamped gradient flow. And if we do both at the same time, then we converge to the original gradient flow. Okay, so we can actually show that we maybe don't always understand what happens in the middle here, but we do understand what happens at the boundaries very well. The second thing we're interested in is long-term behavior. Okay, and we will only discuss setting where we lose momentum because that's the only setting that we fully understand. So as I said before, momentum accelerates our particle, but also prevents convergence to some extent. And the idea, of course, is if we reduce mass over time, we lose momentum over time, and then we may be able to accelerate at the beginning and then converge later. I test this in a deterministic example, where we just try to minimize theta squared divided by 2 using the underdamped gradient flow. And if the mass if we have mass equal to 1, then okay, we can solve the ODE and we get this essentially this exponential thing here with something that oscillates between, I guess, -2, -2 and +2, something like this. That doesn't really matter. But this is what shows what is the solid line here. And we see, okay, we always go down to 0 here because we like hit 0 with this oscillating process or this oscillating part, but then we always go back up. And overall, I mean, we do converge quickly. Yeah, we do converge like e to the minus t over 2. However, if we let mass go to 0 over time, we choose it here as 1 plus t, 1 over 1 plus t. Then actually after 10, at like time 10 is not 10 times, it's actually ODE solution. At time 10, we are already at like 10 to the minus 20. Yeah, so we converge as e to the minus t squared over 2, which it is still not, it would be like superlinear convergence. It's not a quadratic convergence, that would be even faster. But we see here that with a simple idea, we get an extremely fast convergence of this ODE. Okay, and then if we decrease learning rate and mass at the same time, then we get the following limiting theorem. That is under smoothness and convexity assumptions. And we do these two things. Then we do actually converge, so our position of our particle converges to the minimiser as t goes to infinity in probability. The assumptions we have here, and I did not specify them here because even if I show them to you, I mean, they look very complicated. But we did find a setting that works. Yeah, so if we have this like rescaling as square root of t, and with the mass converge to 0 an exponential rate, then this theorem holds for this particular choice of beta and phi m. So interestingly, in this particular setting, we were not able to show convergence if only learning rate decreases, but the mass is constant. We would expect convergence then as well. Okay, because I mean, obviously we need learning rate to converge in SGD to get rid of the randomness, but the momentum is not a problem. Yeah, it just slows down, but it doesn't prevent convergence. But we couldn't show convergence in that setting. Okay, so we would always argue you should lose convergence given these results. Okay, and then I think I just have a few slides left, or like 2 or 3 slides left on discussation and then conclusions. So there's 2 things we need to do when we try to use this in practice. The first thing is we need to sample these index processes, and that's very easy. Yeah, so even the rescaled ones, we can usually give simple Gillespie's algorithms to sample this process I. The bigger problem are these associated second order ODEs. Okay, because I said, okay, we could do Euler, but we shouldn't do Euler because I mean, we do want to get the physics right. And while it's okay, the setting is not conservative, it doesn't conserve energy. So therefore, you would think, okay, I don't need a symplectic integrator, but yeah, I think you should. The other thing is we want to find an integrator that lets us allow two step size independently of m. Okay, because first of all, here in this setting, okay, m even goes to 0. So obviously we don't want the step size go to 0 at the same rate as m, because I mean, in this theory, m went to 0 exponentially. Okay, so we actually want to choose an integrator that is stable, even if m is really, really small. What we can do is, or what usually is being done for these momentum optimization methods is the so-called semi-implicit, is the symplectic Euler method. what we do instead is a semi-implicit Euler method. It's very similar. It's semi-implicit because we are explicit in Q. Yeah, so it's just forward Euler in Q, but we have backward Euler in P. And that's actually no problem at all, because obviously we couldn't use anything implicit here because we will never be able to actually invert these unless it's like linear, but even then you probably wouldn't want to invert these. But with respect to P, we're very simple ODE because I mean this is just a scalar times a vector, and here it's just a vector. Yeah, so this doesn't hurt at all. And we can even rearrange this, and okay, it doesn't look super appealing, but what you can see is actually there's no inversion necessary anywhere. Okay, so we can just write this in explicit fashion, although it's not explicit, but we can write it like an explicit integrator. Yeah, so it's a very simple method to apply. Okay, and then we did apply this in a simple deep learning example. Yeah, where we compare this to normal SG with momentum, and then the setting where we lose momentum and the setting where we have constant momentum. And I will not want to argue that this is a new method only. I mean, obviously this is a theoretical work, and we want to show that you can use these theoretical results. But this is not here to argue that this is the new best method on the planet. Although we got good results here. I mean, probably if you look at this so-called Adam method, you may still get better results. But if you compare just to more basic methods, then this seems to be reasonable, but as I said, that's not the point of the talk. Just one more slide with conclusions, and then I think it's time for the fish restaurant. So we've seen all of these tachometer messages already, but maybe a bit of an outlook. And obviously, what we wanted to study is actually Adam, and not stochastic gradient with momentum. So the difference between stochastic gradient momentum and Adam is that Adam is sort of it's like adapting the step size, you could say. Very basic situation would be has adaptive step sizes, and you could analyze this also in this continuous setting. I'm quite sure you could, but it would be very, very difficult, unfortunately. What would be interesting to me, because I like these constant step size settings where you converge to a stationary distribution, because you can understand these a bit as a regularization of what you are doing. And obviously for stochastic gradient momentum process would be particularly interesting in this constant mass, constant learning rate case, or also maybe decreasing mass, constant learning rate, although then you should go back to SGD. This will be very interesting because this seems to have a large impact in machine learning. And then, of course, everything was convex here. But of course, these methods are especially interesting when you're in a non-convex setting. And that's, I think, all I wanted to tell you. Thank you so much for listening, and I'm happy to answer some questions.